Hello. I hope everyone's doing okay. I'm going to be talking about this work that's joint with Naihui Chia, Andres Guillen, Tongyang Li, Han-Chuen Lin, and Chun-Hao Wang. I'm Yiwen Tang. Just an FYI, we did a major overhaul to this paper recently, and this talk is based on the more recent version. So that version is not on archive at time of recording, but hopefully it will be soon. I'm going to be taking advantage of this medium of the video talk to go a bit faster than normal. So feel free to pause whenever you like. I'm going to be talking about exponential speedups in quantum machine learning. At first glance, many QML algorithms seem to give exponential speedups for useful tasks. For example, the algorithms shown here run in time polylogarithmic and input dimension, whereas classical algorithms typically solve the analogous problems in linear or polynomial time. However, these exponential speedups might not manifest in practice, because unlike their classical counterparts, QML algorithms have to make strong input assumptions and learn relatively little from their output. So on this slide, I've color-coded these applications kind of subjectively to show how close each proposal is to addressing these issues. So these aren't nearly as good candidates as compared to, say, Shor's algorithm for factoring, which achieves an exponential speedup while using the same input and output as classical factoring algorithms. These quantum speedups, these claimed quantum speedups, have long been somewhat mysterious, but recently we've begun to better understand them. In 2018, I showed that the quantum recommendation systems algorithm of Karenitis and Prakash does not give an exponential speedup by describing a classical quote-unquote dequantized algorithm that matches the quantum algorithm up to polynomial slowdown. Subsequent work relies on similar techniques to dequantize a wide range of QML algorithms. And this shows that the advertised exponential speedups of these algorithms disappear if the corresponding classical algorithms can use input assumptions as strong as those of the quantum algorithms. As a consequence, these dequantization results have drastically altered the landscape of potential QML algorithm speedups. There's another recent line of work that unifies essentially all known quantum linear algebra algorithms under a framework called quantum singular value transformation, QSVT. So I'm going to be mostly referring to the Guillen et al. Paper about this. Since QSVT is BQP complete, we probably can't dequantize it in full. For example, the HHL algorithm, which solves a BQP complete problem, can be recovered from QSVT. So it's BQP complete. But one thing that we can notice is that if we look at QSVT based on particular input models, so here I've split our QML algorithms based on which input model they would use in a QSVT version. But if we restrict to QRAM-based QSVT, these examples of hardness don't occur, and they give much more hope for dequantization. So this suggests that it might be possible to dequantize QRAM-based QSVT in its entirety. And this is sort of the fundamental question. And so the answer is that we give a framework for quantum-inspired algorithms based on singular value transformation. And this framework is able to capture the capabilities of QRAM-based QSVT. And it gives strong evidence that quantum linear algebra based on QRAM gives no exponential speedups. We don't prove anything formally, but we prove something for a small case, and I'll show you why we believe that this is good for more general QSVT as well. So in the paper, we show how to use this framework for a variety of things. So we prove the result I just described on a quantum-inspired version of QSVT. We give algorithms for finding expressions for matrix functions of input matrices. And we also can recover prior work on dequantizing QML. And we give a couple new applications. So we sort of unify prior work on quantum-inspired algorithms. So here's a table of the applications that we dequantize. Note that we give new results for the simulating low-rank Hamiltonians result, and we dequantize the discriminant analysis algorithm of Tong and Duan. So all of the algorithms that we get are at least as fast and as general as prior work, the check marks show when we get even faster and even more general algorithms. Okay, so now let's talk about the main results. First, some preliminaries. On the left are some standard definitions. Of note is that for a vector v, I'll use the notation ket v to refer to the quantum state whose magnitudes correspond to the entries of v. On the right here, we define matrix functions in the standard way. So for a scalar function in a Hermitian matrix A, f of A refers to applying f to the eigenvalues of A, which is, in the context of like the eigendecomposition of A. Now, the fundamental idea of the QSVT framework is the idea of the block encoding. So the block encoding is the input model for QSVT algorithms. We say that a matrix A is given by block encoding if we know a quantum circuit implementing a unitary with A as a submatrix, so up to some scaling. What's interesting about block encodings is their compositional properties. So given two matrices via block encodings, we can get a block encoding of their sum, their product, or a transformation of one by a bounded low degree polynomial. And this allows us to get block encodings for a large class of expressions, which we can then apply to a quantum state to get the desired output vector, I guess also in a quantum state. So our fundamental ideas are the same. Given our input matrices and vectors in the right input model, we can manipulate them via sums, products, and smooth function transformations. So bounded low degree polynomials are smooth, so this is a slightly more general notion. This is slightly more general. Then we have our output in our input model, and then so we can get it, we can access it via an output sample. So this input model I'm referring to is that of oversampling and query access. And this is the sort of analog for block encoding that we're going to be discussing. So what is it? Well, let's first define sampling and query access. We say we have sampling and query access to a vector v if in polylog time we can perform the following kinds of queries. First of all, we want to be able to query entries. So if you give me I give you v of I. We want to be able to produce samples according to the distribution specified here. So this is the same as the distribution you get from measuring ket v in the computational basis. This is the same as like importance sampling as well. Finally, we want to be able to query for the norm of v. For a matrix, we say we have sampling and query access to the matrix if we have sampling and query access to its rows, and also sampling and query access to the vector of row norms, little a. You can think of sampling and query access as a classical analog to quantum state preparation assumptions. So by quantum state preparation assumptions, I mean the assumption that you can prepare a state ket v corresponding to an input vector v. This is kind of the same thing. We assume that we have classical access to v, and we also assume that we can get measurements of ket v. Feel free to pause and think about this notion if you have to. So since this is like the sort of essence of the talk. In any case, so it's hard to get sampling and query access to your input in general if you want to have a sublinear time algorithm, because the naive way to do it is linear time. However, if we have our input in QRAM, then we have sampling and query access to it. So QRAM is kind of a fuzzy notion, but we're only going to be interfacing with it classically. So for our purposes, we can just think about QRAM as a data structure. And here we show the standard proposed implementation of QRAM for a matrix, a 2x4 matrix A. And you can see the data structure here. It's like a binary search tree with the entries in the leaves of the tree, and then interior nodes are the sum of their children. They're in the value. So you can see that given a matrix in QRAM, we have sampling and query access to it. The main thing to notice is that we can sample by recursing down the tree with probability proportional to the weight of the node of the child. And so you can really think about sampling and query access as an abstracted version of this data structure. And this abstraction is pretty important, since what we're going to be doing with our composition theorems is basically building more and more convoluted data structures to support these kinds of queries, these sampling and query access queries. Okay. So now we can define oversampling and query access. So for vector v, we say we have oversampling and query access to it. If we have sampling and query access to a v tilde, that's sort of an upper bound on v. So entry-wise, the magnitude of v tilde bounds the magnitude of v. And we also want to be able to query entries of v itself in polylog time. And here, what this parameter is, what this phi is just the norm of our bound. So we know that the norm of our bound is going to be larger than the norm of v, and phi just quantifies how much that is. Similarly, for a matrix A, their definition of oversampling is the same, basically the same. We say we want to have sampling and query access to an upper bound and query access to A itself. Note that for phi equal to 1, oversampling and query access is the same thing as sampling and query access. This notion also has basically the same power as typical sampling and query access. So this lemma says that if we have oversampling and query access to v, we can get sampling and query access. We can respond to the sampling and query access queries as long as we pay an additional factor of phi up to some failure probability and relative error in the norm query. And so this is, you can sort of think about phi as being the cost of post-selection. So this is sort of roughly what's going on here. Okay, now oversampling and query access has the compositional properties that we discussed. So I've given a few examples here. So so for example, given two vectors given access to two vectors, we can get access to their outer product. Given access to a small number of vectors, we can get access to a linear combination of them. Similarly for matrices. And finally, if we have sampling and query access to A and B matrices, then we can get sampling and query access to a matrix M that's close to A dagger B in Frobenius norm. One thing to note, so it's important to keep in mind that this only works for small linear combinations here. And also, if you look at the way that these oversampling constants sort of blow up, you can see that you can see that it's sort of similar to how like a block encoding, the normalization constants of block encodings propagate. If you're familiar with QSVT. So these first three composition properties are pretty easy to see. I'll kind of gloss over them. You basically just need to bound by the right thing, and then you just need to argue that you have sampling and query access to it. So I'll gloss over that. The interesting case is with this matrix product thing. So I'll give a simple example that's not quite as powerful as what we prove. So the idea is that suppose we have sampling and query access to A and B, and we want sampling and query access to A dagger B. So the thing to notice is that A dagger B can be written as a sum of outer products here of rows of A with rows of B. Now notice that since we have sampling and query access to A and B, we have sampling access to the rows of A and the rows of B. And so we have sampling and query access to each of these outer products, right? Using the composition property we just discussed. What we want to use is we want to use a linear combinations property to say that we then have sampling and query access to A dagger B. But this linear combination is over M things, which is too large for us. So what we're going to do is subsample them to get a smaller number of outer products in our sum. So what we're gonna do is we're gonna sample an index, a row index with probability proportional to the row norm of A squared. And then let Z be the corresponding unbiased estimator. And if we compute the variance of this estimator and apply Chebyshev's inequality, we can observe that averaging 1 over epsilon squared independent copies of Z gives us an estimator with a desired error bound with constant probability. And here Z bar is a linear combination of only 1 over epsilon squared outer products now. So we can use our linear combinations protocol to get sampling inquiry access to it. So basically what we did here is we used important sampling sketch to perform dimensionality reduction. So sort of using the classical sketching lingo. This is the idea behind all the big proofs in our paper. And indeed, it's how we get this singular value transformation result. So this is the sort of other main theorem that we use. It's basically saying that if we have sampling inquiry access to A, and we have a function f that's smooth in the desired sense, so f and this f bar are smooth, then we can find a normalized subset of rows, a small subset of rows, such that, and a matrix Z such that R dagger ZR approximates f of A dagger A, which is what QSVT and we call even singular value transformation of A. And this is sort of the runtime here, and this is the dimension of R. Now, this is basically how it's written in the paper, because we sort of need to use it in this form rather than the oversampling inquiry access form. But notice that we can rewrite this R dagger ZR as a sum of outer products. How many outer products? R squared outer products. And R squared is independent of dimension. So we can get sampling inquiry access to our approximation to f of A dagger A. This approximation is in spectral norm, but we could also do Frobenius norm. It's not a big deal. So for some intuition about these constants, we can consider the case where we are working in like the QRAM based QSVT regime. So here, f is a bounded degree polynomial, a bounded low degree polynomial, and the Frobenius norm of A is 1. Then we know that f is smooth in the desired sense. So namely, we can give these bounds on L and L bar. This is by something called the Markov brothers inequality. And this means that basically, and using this bound along with the bound of Frobenius on the Frobenius norm of A, we can get that this runtime here described is polynomial in the desired in the desired parameters. Okay, so finally some discussion. Here's the summary of like the composition properties that we show here. And so we get basically linear combinations, products, and even singular value transformation. And the reason why we say that this is giving evidence that QRAM-based QSVT doesn't give exponential speedups is that this framework coincides with the framework for QSVT when the input is given in QRAM. So in that setting, we could get block encodings of input for QSVT. But as we argued before, we also get sampling inquiry access to the input. And so we can run our classical framework. Further, the matrices are normalized because we're using QRAM, the matrices have to be normalized to have Frobenius norm 1. And when this normalization is like this, then none of our errors blow up. So you saw that just now, actually. And so this is sort of an informal argument why our framework is only polynomially slower than QRAM-based QSVT. And you can see the archive preprint for some more details. Okay, so some final thoughts. What can we conclude from all of this? Well, regarding exponential speedups for QML, I'm not super hopeful. You saw my rough opinion about various proposals in the chart back at the start of this talk. But in general, I think all of the results as of now are pretty speculative. Polynomial speedups are still completely open. In fact, I'm I think our results don't say much about actually the nature of the speedups of QML in practice, because our goal is to match the asymptotics of the quantum algorithm, and this sort of is a very constraining assumption. And we would rather want to use, you know, the modern classical algorithms literature to maybe get something that's different in the asymptotics, but maybe better in practical regimes. Finally, our framework's compositional properties are unusual. I haven't really seen this in the context of like sketching and sampling literature very much. So I'm wondering whether this is like interesting or can be adapted to other problems or other algorithms in the classical literature. Okay, thanks.